There is something coming toward you from the outer darkness. It is not a streak of fire across your sky, not yet, but an inevitable fall. Astronomers have given it a name, Bernardinelli Bernstein. Most of them just call it BB. You could think of it as a comet, but that word feels too small. BB is so massive, it makes every interstellar visitor you have heard about look like a pebble. It stretches roughly 137 kilometers across, and it is about 10,000 times more massive than 3I Atlas. You live in a time when telescopes can catch something like this long before it becomes a bright object in the sky. On a monitor in a quiet control room, BB is just a faint, measured smear of light. But behind that tiny smudge is a story that reaches back to the birth of the solar system. Scientists say BB is a time capsule, a frozen relic that has been falling inward for millions of years after spending billions of years in the dark. Others are less comfortable. They look at its size, its orbit, its timing, and quietly ask a different question. Why now? You already know 3I Atlas as a strange visitor, small, fast, and confusing. It came from another star system, raced through the inner regions, and left you with more questions than answers. BB is the opposite in almost every way. Where Atlas was fragile, BB is colossal. Where Atlas rushed through space, BB moves with the slow authority of something that has always belonged here. It is not an outsider passing through. It is one of your own system's ancient worlds, a leftover core that somehow ended up buried in the distant Oort Cloud, only to begin its long descent, just as your species learned how to watch. That is the part that makes people uneasy. The Oort Cloud is supposed to be a quiet cemetery of ice and dust, a place where frozen bodies drift on stable orbits for billions of years. BB does not look small. It does not look lazy. It is big enough to blur the line between comet and dwarf planet, structured enough to suggest an interior shaped by gravity and time, and already active at distances where almost nothing should wake up. Something nudged this giant. Something disturbed a region of space you barely understand. As you listen tonight, you are not being asked to panic. BB will never come near your world. Its closest approach to the Sun will be far out beyond Saturn. For Earth, this is not a story of danger. It is a story of what it means when a hidden piece of your own past suddenly rises out of the dark. Because if an object this large can be shaken loose, then the outer reaches of your system are not as quiet as you were taught to imagine. Stay with this journey and you will see why many astronomers call BB the most unsettling object they have studied. You will follow its path backward into the Oort Cloud, where galactic tides, passing stars, and perhaps unseen masses might have conspired to wake it up. You will look at its strange perpendicular orbit, its layered planet-like interior, and its early activity far from the Sun. You will hear about ideas that stretch from hidden planets to dark matter structures, and about how all of them intersect in this single, silent body drifting toward the light. Most of all, you will understand why this object feels far more sinister than 3I Atlas. Not because it threatens your survival, but because it quietly breaks the picture of a safe, simple solar system. BB suggests that your home is wrapped in a shell of ancient, half-formed worlds, any one of which could be nudged inward without warning. Tonight, you are here, listening. At the moment, your instruments have found one of them. You are watching the universe reveal a secret it has kept for 4 billion years, and you have time to sit back, breathe, and let that realization settle in as BB continues its slow fall toward the Sun. You first meet Bernardinelli Bernstein, the way the scientist did, as a faint mark buried in old data from the Dark Energy Survey. Not a spectacle or a dramatic flash, just a single moving point that didn't belong where it appeared. When the team traced that point backward and forward through the archive, something became clear almost immediately. This was no ordinary comet. Its orbit was enormous, its distance extreme, and its brightness far too high for something supposed to be small and quiet. Nothing about it matched the familiar behavior of the little ice bodies you've seen illustrated in books or documentaries. As researchers recalculated its orbit, refined its distance, and compared its brightness across images, a number began to form. Then another, until the truth settled into place. This nucleus is about 137 kilometers wide. You can picture that if you imagine an entire metropolitan area, edge to edge, made of ancient ice and dark rock. Typical comets measure only a few kilometers. Even the giants you occasionally hear about rarely crack 10 or 20. BB, by contrast, crosses the threshold into another category entirely. It is big enough for its own gravity to pull it into a rounded shape, something that only happens when an object is more like a small world than a drifting snowball. If you compare it with 3I Atlas, the visitor that captured so much attention with its strange behavior, the difference becomes even sharper. Atlas is tiny, fragile, a sliver of material from another star. BB outweighs it by a factor of roughly 10,000. Where Atlas seemed to drift like a lost seed, BB moves like a silent boulder, falling through the dark. Every time you look at the numbers, the scale presses deeper. This is not the remains of a crumbling leftover. This is the frozen core of something that nearly became a planet and then never got the chance. You would expect an object like this to be cold and dormant, at 20 astronomical units from the Sun, where the light is faint and the temperature hovers near absolute stillness. Even the most volatile materials should remain frozen solid. And yet BB began to brighten. Its coma, its thin envelope of gas, started forming long before water ice could possibly sublimate. Something else was waking it up. The best explanation is carbon monoxide and other hypervolatile compounds, the kinds of materials that evaporate at temperatures far lower than water ever could. These gases tell you something about BB's interior. They tell you it has preserved ingredients from the earliest days of the solar system that have not been heated, altered, or stripped away. You begin to understand why astronomers use words like relic and primordial. BB is ancient in a way that few things near you are. It carries layers of frozen chemistry untouched for nearly 4.5 billion years, formed back when the Sun itself was still gathering mass. As you listen, you get the feeling that you're not studying a comet. You're looking at a survivor from a time when worlds collided, migrated, and scattered like debris across a young and violent system. BB is one of the pieces that never found a home. The more you consider its shape, the more the picture sharpens. Smaller comets are irregular, lumpy, fragile. BB's rounded body signals internal strength, the weight of gravity acting over immense timescales. Its surface may hold cliffs, fractures, or plains shaped by ancient outgassing. Its interior is likely layered, as if you sliced open a small world that stopped growing halfway. When scientists say this is the largest comet nucleus they have ever seen, by far, it isn't exaggeration. It is a recognition that the usual categories do not apply. You are observing something oversized for its class and undersized for its potential, suspended in a strange middle ground between comet and dwarf planet. As BB moves inward, slowly, predictably, its size becomes more than trivia. Size means inertia. It means stability. It means that whatever shifted its orbit had to act on an enormous mass. Comets only a few kilometers wide can be jostled by mild gravitational nudges, or slight interactions with passing bodies. A 137-kilometer nucleus should resist those disturbances. It should stay where it has been for billions of years. But BB did not. Something perturbed it strongly enough to send it drifting toward the light. You feel a quiet kind of amazement settle in. There's no fear in that feeling, only the awareness that you're looking at a rare glimpse of your solar system's early architecture. BB is not interesting because it threatens anything. It is interesting because it is honest. It shows you what your system was made of before planets became planets, before orbits stabilized, before the outer darkness filled with quiet debris. If you understand BB, you understand a chapter of your home's history that usually remains sealed behind time and distance. As you connect these pieces, its size, its activity, its ancient composition, you begin to see why this object matters so much more than Atlas. Atlas was a mystery. BB is an explanation. It tells you that your solar system is edged with material far larger and more complex than you were taught to imagine. It reminds you that the Oort Cloud may hold dozens of worlds like this, waiting silently, undisturbed until something shifts them. You're not looking at a snowball. You're looking at the frozen core of a world that never finished becoming a planet. In that realization, the story becomes deeper, because if an object this massive can be moved, and if it woke up now, then something out there has the strength to shape giants, not just dust. This is the largest comet nucleus we have ever seen by far. The kind of statement that sounds simple until you understand the weight behind it. But the question that keeps astronomers awake at night isn't how big it is. It's why it woke up now. When you first hear the number attached to BB's orbit, millions of years, you feel a kind of distance that almost protects you. It seems too slow, too large, too far away to matter. But then the question arrives, quiet and persistent. Why now? Why in the brief window of human civilization, in the thin slice of time when you have telescopes capable of detecting it, does this giant decide to fall inward? If it had drifted a million years earlier or later, it would have passed unnoticed, hidden in the outer dark. Yet here it is, entering the reach of your instruments during the one moment in the history of your species when you know how to look. To understand that, you have to return to the structure that holds BB, the Oort Cloud. You can imagine it as a spherical shell wrapped around the solar system, extending far beyond the planets. It is not dense or glowing or sharp-edged. It is more like a vast, fragile halo made of icy bodies formed during the birth of the planets and flung outward by gravitational encounters long ago. Every object inside it moves slowly, so slowly that a complete orbit might take millions of years. They drift in quiet patterns, preserving the chemistry of a world before worlds. This region should be calm. It should be stable. That is why BB's motion raises questions. For an object this massive, stability should be the default state. Small comets can wander. They can be nudged by small forces and knocked into the inner system. BB is different. With its size and weight, its orbit should resist random motion. Something needed to act on it, and that something had to be unusually large or unusually precise. When you think about the enormous span of time BB has spent in the Oort Cloud, billions of years, you realize how unlikely it is that such a body would be disturbed unless a genuine event occurred. That is the root of the curiosity pressing against you. Scientists often point to three major suspects. The first is the galactic tide. Your solar system does not float in isolation. It is inside the disk of the Milky Way, swinging gently around the galactic center every couple 100 million years. As it moves, the gravitational pull of the galaxy rises and falls, like a slow swell passing beneath a ship. These changes are tiny but constant. Over long periods, they can slightly stretch or compress the orbits of Oort Cloud objects. For small comet nuclei, this can be enough to set them drifting inward, but for something as large as BB, the effect should be negligible. The tide alone is not a satisfying explanation. The second suspect involves passing stars. The Gaia mission has revealed that throughout the Sun's history, other stars have passed relatively close. Not close enough to threaten the planets, but close enough to brush the outer edge of the Oort Cloud. Even a distant star can have gravitational influence if it moves slowly enough relative to the Sun. One such star, Scholz's star, is believed to have skimmed the outskirts of the cloud about 70,000 years ago. Others have come even closer in deeper time. For small comets, these stellar flybys can be significant. For BB, though, any star powerful enough to move it would have needed to pass at a rare angle, with a rare velocity, at a rare moment. It is not impossible, but it begins to feel like a coincidence too neat to accept without further evidence. The third suspect is diffusion, the slow drift of orbits due to countless tiny influences acting over immense spans of time. Orbits are rarely perfect. Even subtle gravitational disturbances accumulate. Over billions of years, a body can wander from its original position through what scientists call chaotic diffusion. For a small object, diffusion can explain strange paths and unexpected motions. For BB, the theory struggles. Something this big does not diffuse easily. Its inertia is too strong. Its orbit too deeply rooted in its original momentum. Random walk alone does not tell the full story. As you weigh these options, a picture forms. The usual mechanisms feel too small for an object this large. Galactic tides are too soft. Diffusion is too slow. Passing stars are too rare in the exact configurations needed. For BB to wake up, the push had to be special. It had to be sharp enough or well-timed enough to stir something that had been asleep since the beginning of your world. When you consider this, the timing begins to feel less like chance and more like the clue itself. You can almost see the scene in your mind, a quiet Oort cloud drifting in perfect stillness for billions of years, its icy bodies untouched. Then, suddenly, one giant begins to move. It falls inward on a long, slow arc that will eventually bring it into the light. As it travels, you realize that this motion began before your species existed, long before the first tools or first words. BB has been falling for millions of years, and yet you are here at the precise moment it becomes visible. The scale of that timing reshapes your sense of the story. Timing, in celestial mechanics, is often the loudest clue. That line echoes the core of the mystery. It reminds you that BB's arrival is not merely about what it is, but when it shows itself. By the end of this part of the journey, you feel the shift. You have moved from understanding the object to questioning the event that moved it. And those questions will lead you into deeper territory, toward ideas involving hidden planets, dark matter structures, and long-forgotten encounters that might have changed the outer edge of the solar system. We'll test different suspects. To see how unusual this timing really is, we have to look at the path this object is taking. When you picture the solar system, you probably imagine a flat, calm disk. Planets circling the Sun on tidy paths, most of them tilted only a little. The giants sweep around at a slight lean. The smaller worlds tilt more, but still stay within the sense of a shared plane. Even long-period comets, with all their eccentric loops, tend to honor this broad alignment. They may dive in steep, but very few cut almost straight through the system at a right angle. That is why BB's orbit stands out the moment you see it drawn in 3 dimensions. Its inclination is roughly 95.5 degrees. If the solar system is a table, BB is dropping in from just above the edge, slicing down through the middle, and arcing out the opposite side. It does not glide along with the other worlds. It crosses them. It feels less like a member of the family and more like an unexpected visitor walking across the room. In dynamics, that angle is a loud statement. It tells you that this object has not always lived a quiet life. Something powerful acted on it. Something changed its motion in a way that nearly flipped its path. To appreciate this, you can compare it with the ranges you know. The major planets orbit within about 30 degrees of the same plane. Even the odd ones out, like Mercury with its 7 degrees, or Pluto with its 17, are still part of the structure shaped by the original disk of dust and gas. Typical comets can reach higher inclinations, sometimes 30, sometimes 40, sometimes more. But near 90 degrees, the population thins dramatically. Few objects of any size take orbits that nearly stand upright relative to the rest of the system. Almost none of them are as large as BB. That size matters. Smaller bodies can be tossed around by gravitational interactions. It takes only a slight push at the right moment for a small comet to end up with a strange tilt. But a 137-kilometer body requires a far larger force to change its direction so dramatically. Whatever event shaped BB's orbit was not gentle. It left a mark so deep that the tilt has persisted for millions, perhaps billions of years. And as one orbital theorist likes to say, orbits remember their past even when the objects forget. This brings you to the two main explanations scientists discuss. The first imagines BB as a native of the inner solar system's early chaos. In that era, planets did not yet follow orderly paths. They fought over space, scattering smaller bodies in all directions. A close brush with a forming giant planet, or a collision with another large planetesimal, could have flung BB outward with enormous energy. If the angle were just right, BB could have been launched almost sideways, climbing up to a steep, near-perpendicular orbit before drifting into the long exile of the Oort Cloud. This scenario paints BB as a survivor of the solar system's violent youth, a piece of a world thrown outward like a shard from an explosion. The second scenario is more exotic. It imagines BB as an outsider, a body that formed around another star entirely. In that picture, BB drifted near the young sun during a moment when both stars were part of the same stellar nursery. The sun's gravity captured it, pulling it into a distorted, awkward orbit. Over time, that orbit would have settled into the outer reaches, preserved as the sun drifted away from its birth siblings. This idea places BB among the class of objects that were not born here, but adopted, stored in the Oort Cloud with the debris of many origins. Though Atlas came from interstellar space briefly and left again, BB could be an interstellar visitor that never escaped. Both explanations share one thing: a significant shock in the past. Whether the blow came from a giant planet in its early growth or from the gravitational tug-of-war between two young stars, the orbit BB follows today is evidence of a major event, and you can feel that history in the geometry itself. It is not just visiting your planetary plane, it is cutting across it, like a blade. As you imagine this object sliding inward, the visual becomes even more striking. You see the planets moving in their calm circle, each one following the gentle curve of the ecliptic. Then you see BB's path descending almost vertically, a long arc from the top of the diagram down toward the sun. It feels less like a normal orbit and more like an intrusion, a reminder that your solar system is not as orderly as it appears on classroom posters. The dynamics are complicated, the past is messy, and the objects that inhabit the outer darkness carry scars of that mess. What kind of event throws a world onto a path like this? That question becomes the hinge of this chapter. You know the usual forces, tides, diffusion, passing stars, are too weak for a body this large. You know the angle is not something that happens casually. Something dramatic carved this orbit. And now, after ages of quiet, you are finally seeing the consequences as BB falls inward again. Its steep inclination offers a clue for later discussions. It hints at past interactions with something massive. It hints at forces on the edge of your understanding. It hints that when you examine BB's history closely, you might uncover signs of hidden planets, dark perturbers, or ancient stellar encounters. You begin to sense that the orbit is not just a path through space. It is a record, a fossil, a scar. By the time you reach the end of this part of the journey, the feeling shifts again. Earlier, the scale of BB made it unsettling. Now, its history does. You're no longer looking at a quiet relic. You're looking at a witness to an event powerful enough to throw a world off the system's plane, lock it into a long arc far above and below the sun, and send it drifting for millions of years before arriving in your era. And despite that violent past, it is still bound to the sun. Whatever its origins, whatever shaped its trajectory, it belongs to your system now. To understand what kind of world could survive such a violent past, we have to look beneath its surface. When you picture a comet, you probably imagine something irregular, jagged, a lumpy shard of ice and dust that drifts without structure. BB is nothing like that. Its gravity is strong enough to pull itself into a rounded shape, giving it the appearance of a small world rather than a fragment. That simple detail tells you something important. This object is not debris. It formed with enough mass and integrity to become nearly spherical, which means its interior has been shaped by slow, persistent forces across billions of years. You are not looking at a loose pile of material. You are looking at a compact, layered body with its own internal architecture. Those layers begin at the surface, where a hardened crust of dust and ice shields what lies beneath. Over time, the outer shell darkens under cosmic radiation, transforming into a tough rind. Below that crust is a mixture of water ice and complex organic materials, the same ingredients that filled the early solar system. In deeper regions, the temperatures are colder still, cold enough for frozen carbon dioxide to remain locked in place. And at the core, scientists suspect pockets of carbon monoxide and other hypervolatiles remain sealed under pressure, waiting for even a small amount of heat to set them free. You see hints of this structure in the fixed jets observed from BB. Even at great distances, the object releases gas from specific points rather than randomly across its surface. These active regions behave like openings to deeper layers. Their stability suggests the venting is driven by geometry, not chance. Something inside warms slightly, pressure builds, and gas escapes through the same old cracks each time. In that behavior, you begin to recognize the physics of cryovolcanism, the cold equivalent of volcanic activity. Instead of molten rock bursting from underground chambers, you have frozen gases accumulating until they find a path to the surface. It helps to imagine a frozen volcano that hasn't erupted in 4 billion years, and then, suddenly, something warms it up. The heat doesn't need to be dramatic. Just a small increase in temperature as BB inches closer to the sun is enough to loosen material that has been locked in place since before Earth formed. When those deep pockets of hypervolatiles expand, they force their way through fractures, lifting dust and ice in narrow plumes that drift into space. This is not speculation without precedent. You have seen similar activity on the icy moons of the outer planets. Enceladus, for example, sends fountains of water vapor into the void from long fractures along its south pole. Triton, orbiting Neptune shoots nitrogen geysers from its surface when sunlight warms dark patches of ice. These bodies are larger and more active than BB, but the underlying principle is the same. Cold worlds can breathe. They can hold internal pressure. They can rupture, vent, and reshape themselves, even when temperatures fall far below anything familiar. Now imagine BB in that context. It is not a moon orbiting a giant planet. It is not warmed by tides or subsurface oceans. It is a solitary worldlet drifting through the dark, carrying the ingredients of ancient chemistry. The fact that it shows any activity at all, and does so from the same locations over time, suggests that its interior is organized. It has layers, it has pockets, it has structure. You are not watching a dead object. You are watching something that responds to its environment, slowly and quietly. This is where the story gains a touch of the unexpected. For an object this old, this far from the sun, you would expect absolute silence. Instead, you see signs of internal tension. As BB approaches the warmer regions of its orbit, stress will accumulate along its crust. The vents might widen, new fractures might appear. In extreme cases, a body like this can split, shedding pieces of itself into space. That possibility carries both a sense of loss and a sense of opportunity. If BB were to fragment, each shard would reveal information from deep inside, offering scientists a rare look at materials that have remained sealed for billions of years. These objects are not just debris, they're unfinished worlds. That idea becomes clearer the more closely you examine BB. Everything about it suggests potential halted by circumstance. It began as a planetesimal, one of many building blocks that once collided and merged to form planets. It simply never found a partner large enough to continue that growth. Instead, it was thrown outward, preserved in the cold, waiting in the dark as the solar system matured without it. Only now, as it approaches the sun again, do you have the chance to see the layers and structures that froze into place all those ages ago. When you shift your perspective this way, BB transforms from a curiosity into a kind of museum exhibit from the dawn of the solar system. Its crust holds the chemistry of the first billion years. Its interior traps the volatile gases that powered the earliest reactions. Its shape marks the moment when gravity began to pull clumps of matter into organized forms. It is both primitive and complex, fragile and massive, quiet and active. It is a paradox that makes sense only when you recognize it as something that almost, but not quite, became a planet. And this unfinished world is not drifting in place. It's slowly, steadily falling toward us. Right now, as you sit comfortably under your own sky, BB is still far beyond anything familiar. It is not near Jupiter, not near Saturn. It is still outside the region shaped by the giant planets, drifting in from the cold frontier beyond Neptune and Uranus. At that distance, sunlight is weak, the temperatures are brutally low, and BB looks like a quiet ember in a dark room. Yet every year, it draws a little closer, slowly, predictably, inevitably. When you trace its timeline inward, the numbers settle into place. Its closest approach to the Sun will occur around the year 2031, when it reaches a distance of roughly 10.9 astronomical units. That puts it just beyond Saturn's orbit. It will not come anywhere near Earth, nor will it disturb the planets. For your world, BB poses no danger at all. You are safe. And yet, even at that distance, the science it carries is extraordinary. The years between now and perihelion form a kind of countdown. This is the moment when BB is still relatively exposed, before its coma thickens into a bright shell of gas and dust. Right now, you can still study the surface. You can still measure jets directly and model the composition of material that vents from its interior. in a few years, that opportunity will begin to fade. As the object warms, the gases it carries will build into a dense atmosphere that obscures the core. Once that happens, the window to examine its bare structure will close. These next few years are special. They are the one time when you can watch a giant planetesimal awaken from hibernation. With each passing month, stress from the sun's gentle heat will work deeper into its layers. The vents may widen, the surface may fracture. In extreme cases, chunks may break away. Large bodies like BB do not always crumble, but the possibility exists, especially when internal pressure mixes with rising temperature. If it fragments, the core becomes even harder to study, replaced by a cloud of drifting debris. Scientists know this. They know that inactivity is temporary, that stress is building quietly. That is why the timeline matters. BB is not on a collision course with Earth, but it is on a collision course with human curiosity. If you do nothing, if you simply watch it drift by, the story ends without you learning what this object truly is. You have only one chance to examine a world like this in its raw form. Once it swings around the sun and heads outward again, it will vanish into the cold for millions of years. By the time it returns, your species will be long gone. This is a once-in-civilization chance. Once it's gone, it's gone. That realization brings two emotions at once. The first is relief. You do not have to fear BB. It will not harm your planet. No apocalypse, no impact. The second is a quiet, heavier feeling. The knowledge that missing this opportunity would be one of the great scientific regrets of the century. You live in the only era in the history of your species when this object is close enough to study. You are here at the one moment when a frozen world from the edge of the solar system drifts close enough to reveal its past, its chemistry, its structure, its secrets. Our species will only see this object once. You can sense the slight urgency beneath the calm description. Scientists know that the closer BB gets, the more active it will become, and the harder it will be to observe its true core. They also know that long-period comets like this one sometimes break under thermal stress. If BB remains intact, the view will be remarkable. If it fractures, the science will change. Either outcome is meaningful, but only if you are prepared. The object will not wait for you. It will follow the path carved for it millions of years ago. So the question begins to form in the back of your mind. Will humanity merely watch it pass, or will you reach out and meet it? That question carries forward into the next discussions, where the idea of sending a mission becomes more complicated than you might expect. For now, you can hold the thought gently. You are living in the right decade, at the right moment, to witness something ancient inch toward the sun. BB is drifting inward, slow enough to watch, but fast enough that you can feel the countdown. You can almost imagine it from a satellite's perspective. A massive, dark sphere turning slowly as faint sunlight glints off its surface. It is not a threat, it is a lesson. And if you pay attention, it will show you parts of the solar system's history that have remained hidden for most of human existence. And this object is not alone. It's part of a pattern that's been quietly emerging in our sky. When you zoom out from BB and look across the past decade, something begins to shift in your understanding. BB is massive, ancient, and unsettling, but it is not appearing in isolation. It is part of a sequence, a quiet chain of unusual visitors and unexpected behaviors that has unfolded almost back to back. One anomaly is a curiosity. A chain of anomalies begins to look like a signal, and as you listen, you start to feel that signal forming. The pattern began in 2017, when a faint streak of light swept through the solar system on a path unlike anything seen before. That object was Oumuamua. the first confirmed interstellar visitor. It showed no coma, no steady release of gas, and yet it accelerated slightly as it moved away from the Sun. A rock or an iceberg should not behave like that. You learned then that the universe was not as tidy as your textbook suggested. Oumuamua came and went quickly, leaving behind more questions than answers. 2 years later, in 2019, came 2I Borisov. Unlike Oumuamua, Borisov behaved exactly as a comet should. It released gas. It produced a coma. It looked normal, except for one detail. It was interstellar too. 2 visitors from other stars in such a short time felt like a statistical surprise. Borisov reassured you that interstellar bodies could follow familiar rules, but it also reminded you that the space between stars is more populated than you once imagined. Then came 3I Atlas in 2025, small, faint and fragile, yet full of contradictions. It activated too early. Its glow behaved strangely. Its mass loss made little sense. Its chemistry raised eyebrows. Atlas was not threatening, but it was puzzling. It stretched the limits of what scientists understood about icy bodies passing through the inner system. If Oumuamua was a mystery and Borisov was the control sample, Atlas was the outlier that refused to fit cleanly into either category. And now there is BB, enormous, bound to the Sun, tilted nearly perpendicular to the planetary plane, and active from distances where most comets sleep. The others came and went. BB belongs to the solar system. The others were small and fast. BB is massive and slow. The others were visitors. BB feels like a revelation. It anchors the pattern instead of drifting through it. When you look at all 4 objects together, a pair of questions emerges. The first is simple. Are you noticing these bodies only because your technology has improved? Modern surveys can catch faint objects that older telescopes would have missed entirely. The deeper and wider you look, the more anomalies you should expect. That is the natural explanation. The second question is harder to ignore. Is the outer solar system genuinely more active than it used to be? Are these objects appearing now because something has begun to stir them? You do not have to choose an answer yet, but the timing feels unusual. The diversity feels unusual too. In less than a decade, you saw a tumbling interstellar shard, a textbook interstellar comet, a small but perplexing visitor with strange chemistry, and now a colossal worldlet falling inward on a path carved by an ancient shock. These objects do not resemble one another, yet they share a theme. Each challenges an assumption about how the solar system interacts with the universe around it. This is where BB becomes more than just another name on the list. BB is the one object in the pattern that demands a deeper cause. Its mass makes it resistant to small nudges. Its tilt requires a powerful event. Its timing hints at something deliberate in the physics, even if the event itself was purely natural. If 3I Atlas is the mysterious visitor, BB is the sinister anchor that pulls the whole trend into focus. It is too large to ignore, too strange to dismiss as coincidence, too old to fit neatly into the models built from smaller comets and short-period fragments. As you listen, the perspective widens. You begin to wonder how many other BB-sized bodies wait unseen in the Oort Cloud, preserved in darkness, drifting on long orbits that never bring them into view. The outer shell of the solar system could contain hundreds of worldlets like this. Most will never fall inward. Some will. And when they do, they tell you something about the invisible forces shaping your system from the outside. This line of thinking leads naturally toward larger ideas. Hidden planets, dark perturbers, unseen gravitational structures, interactions between your sun and the galaxy around it. BB is a clue, not a warning, not a threat. but a sign that the architecture of your solar system is more dynamic than it appears from the comfort of the inner regions. The pattern unfolding in these recent years suggests a quiet conversation happening at the edge of your world, a conversation you are only now able to overhear. Maybe your instruments are simply better. Maybe you are finally paying attention. Or maybe the solar system is passing through a chapter where ancient objects are being nudged, stirred, and drawn into the light. That possibility lingers, not ominous, but curious. You are living during a time when these stories are becoming visible, when your species has the tools to catch faint visitors and interpret their paths. You find yourself thinking, maybe there is a hidden architect behind these coincidences, not an agent or intention, but a gravitational structure, a forgotten interaction, or a mass you have not yet mapped, something that could explain why this pattern is unfolding now. Something strong enough to shape the path of BB itself. So if there is a hidden hand shaping these orbits, what could it be? When you try to understand what could push an object as massive as BB off its stable orbit, you eventually reach a set of ideas that sit at the edge of modern astronomy. Not fantasy, not fiction, but the zone where limited data meets real possibility. This is the domain of Planet 9, phantom perturbers, and exotic objects that may still hide in the distant dark. None of these ideas are proven. All of them come from attempts to explain motions that do not make sense without something else exerting a pull. The most familiar of these possibilities is Planet 9. The hypothesis goes back years, sparked by a strange pattern in the orbits of very distant trans-Neptunian objects. Instead of spreading evenly in all directions, their paths seem to cluster, pointing roughly the same way, leaning in similar directions, as if shepherded by a massive object far beyond Pluto. The simplest explanation is a super-Earth, a planet 5 to 10 times the mass of Earth, flung outward during the early chaos of the solar system. In this scenario, Planet 9 circles the Sun on a wide, elongated orbit, taking thousands of years per revolution, quietly shaping the outer regions without ever coming close to the inner system. If such a planet exists, it would have enough mass to sculpt the scattered disk, tilt distant orbits, and influence bodies that drift near its path. You can imagine it like a heavy marble resting on the edge of a table covered with lighter beads. Even if the heavy marble never moves much, the beads respond to its presence. Their paths curve, their alignments shift, their orbits remember. That is the logic behind the model. But Planet 9 is not the only explanation scientists consider. Some propose that instead of a single large body, a massive but diffuse disk of small objects could create a shepherding effect at the edge of the solar system. Countless tiny gravitational pulls acting together over millions of years might mimic the influence of a single planet. It would be subtle, fragile, and hard to detect directly. But it would fit the data if the distribution of material were just right. Others consider more compact perturbers, dark objects that do not reflect light. One idea involves a primordial black hole, a remnant from the earliest moments after the Big Bang, no larger than a grapefruit, but as heavy as a mountain. Such an object would be nearly impossible to detect without extremely close observation. Yet its gravity would be unmistakable. Another idea involves clumps of dark matter, aggregates of invisible mass that could pass through the outer solar system without interacting with light at all. These are not mainstream conclusions, but they remain mathematically viable because gravity allows them. Where does BB fit into this landscape of possibilities? Through its orbit. If you rewind BB's path millions of years, you find it drifting quietly in the Oort Cloud, stable and calm. Something pulled it off that path, something strong, something that did not just nudge a small, fragile comet, but shifted a world-sized body with deep inertia. Galactic tides alone are too weak. Passing stars are too rare in the right configuration. Slow chaotic drift can't explain such a dramatic tilt. That leaves you looking at perturbers, massive, distant influences that can reshape orbits without ever leaving a visible trace. That does not mean Planet 9 exists. It does not confirm a hidden planet or a dark object. It only tells you that BB responds in a way consistent with being disturbed long ago by something large. And this pushes you into a strange middle zone between what you can see and what you can measure. A region where mathematics is firm, but the evidence is incomplete. A region where imagination is necessary, but only within the rules of physics. Sometimes the best evidence for a hidden planet is written in the orbits of the objects it disturbs. That thought lingers as you consider BB's path. 95 degrees, nearly perpendicular, large enough to resist small forces, ancient enough to have seen the solar system evolve through epochs. If something once tugged at it, whatever did so must have been impressive. BB may carry the scar of that event. This is where the wonder softens into something more reflective. You begin to feel the scale of the environment your solar system lives in. You picture the sun drifting through the galaxy, passing through regions of different density, brushing past invisible structures that may pull gently on the outermost bodies. You imagine ancient encounters with young stars from the sun's birth cluster, each one capable of leaving subtle distortions in the Oort Cloud. Perhaps Planet 9 exists. Perhaps a phantom perturber drifted through the outskirts long ago. Perhaps the shaping event is something you have not yet considered. And there is a twist. It is entirely possible that no massive perturber exists at all, that the clustering of distant orbits is statistical noise, that chaos alone explains the past. If that is true, then the solar system is even harder to predict than the big planet theory suggests. In some ways, that is an even more unsettling idea. A cosmos where massive bodies can drift inward simply because of slow, unpredictable motion over immense timescales is a cosmos without simple rules. But whatever the truth, BB forces you to confront the question. It is too large to dismiss, too tilted to ignore, too old to have arrived here casually. Something shaped its path. And if you understand that something, you might understand why this ancient worldlet is entering the inner regions now, in the era of telescopes and surveys, when humanity is finally able to watch. To see what has been disturbed, we need to look at what BB itself really is, a dwarf planet in Comet's clothing. When you look at BB's size, shape, and behavior, a quiet realization begins to form. This object is not just a comet. It is not even close. In many ways, BB fits more naturally beside the smallest dwarf planets than beside the icy fragments that usually drift into the inner system. Think of bodies like Hygeia, or some of the mid-sized Kuiper Belt worlds, objects large enough for their gravity to round them into spheres, but too small to ignite geological drama the way Pluto or Eris do. BB lives in that same mass range, yet it appears in a place no dwarf planet has any business being, falling in from the farthest shadows of the Oort Cloud. When you compare their sizes, the resemblance becomes clear. Most comets are only a few kilometers across. The giants of the Hale-Bopp class reach tens of kilometers. BB stretches to roughly 137. That is dwarf planet territory. A body that size has enough gravity to smooth out its surface, to erase the irregularities that mark rubble piles, and to pull itself toward equilibrium. In other words, BB meets one of the quiet criteria for being considered a world, and there is more. The activity you see, the jets from fixed locations, the stable regions of outgassing, suggests that BB has internal structure, something layered, something preserved, something that holds volatiles the way a small world would, not the way a loose cometary fragment would. You get the impression of a differentiated interior, a crust hardened by cosmic radiation, a mid-layer rich in water ice and organics, deeper zones where carbon dioxide remains frozen, and a core that still holds ancient pockets of carbon monoxide and hypervolatiles. That is not the anatomy of debris. That is the anatomy of an unfinished world. The story of how it became unfinished adds a quiet sadness to the picture. In the early solar system, planetesimals like BB collided, merged, and fought for survival. Some grew large enough to become planets. Others lost that race. BB may have been one of those candidates, on its way to growing larger, drawn into the chaos of early formation, until a gravitational encounter sent it flying outward. It never gathered more mass. It never had the chance to melt, differentiate fully, or evolve the way a true planet would. Instead, it was exiled to the outermost darkness, locked in a region where the sun is only a distant star. So BB is a dwarf planet wearing a comet's mask. It carries the ingredients of a world that almost was, drifting through the cold for billions of years, waiting for the moment when a slight nudge would send it falling back toward the sun. As you listen, you start to feel something surprisingly gentle, a sense of sympathy for this forgotten world. It was cast out before the solar system finished forming, denied the warmth and light that shaped the planets you know so well. Now, as it drifts inward, you are witnessing its brief return from exile. This perspective reshapes your sense of the Oort Cloud itself. Traditionally, it is described as a swarm of icy fragments, small, irregular leftovers from the birth of the solar system. But if BB exists, perhaps it is not unique. Perhaps the Oort Cloud hides a whole zoo of small worlds, frozen spheres that started down the path of planetary growth but never reached their destination. There might be more dwarf planets in the dark than in the light, more worlds waiting in the cold than orbiting where you can easily see them. It is a thought that feels both haunting and beautiful. As you sit with that image, the motif returns like a refrain. Unfinished world. You have heard it before, and you will hear it again, because it captures something essential about BB. It is incomplete by nature, yet complete enough to carry the record of the early solar system. It is massive enough to be coherent, yet fragile enough to break when warmth reaches its crust. It is ancient enough to be a relic, yet active enough to breathe faintly into space as it falls inward. BB is a planet that almost was, and a mystery that still is. Then comes an unsettling implication. If BB is typical rather than exceptional, the Oort Cloud might be far more complex and far more dangerous than anyone assumed. If many objects in that region are world-sized, then the dynamics of the outer system are governed by far more mass than scientists have accounted for. That is not a threat to Earth, but it is a challenge to understanding. It means that what you see now, a single giant drifting inward, could be only one example among many, most of them destined to remain invisible forever. This is where the tone softens into something closer to awe. BB is not just sinister in the scientific sense, it is also beautiful in its loneliness. It carries a kind of melancholy, the feeling of a world built from the same materials as your own, cast out before it had the chance to become anything more. And now, by coincidence or fate or simple orbital mechanics, it passes through the one era when humans are able to watch it do so. And whenever a world feels this strange, some minds inevitably ask, what if it isn't natural at all? Whenever an object behaves strangely, whispers, follow. BB is no exception. You hear them online, in small discussions, in quiet comments beneath astronomy posts, questions half serious, half curious, never loud, but always lingering. People notice the fixed jets. They notice the smooth light curve. They notice the peculiar orbit. And they wonder softly, what if this isn't natural at all? Those thoughts come from familiar patterns. A jet that always appears in the same place might look like a thruster. A light curve with almost no variation could be mistaken for a controlled rotation. An orbit tilted nearly perpendicular to the solar system might feel like an approach angle rather than an accident. When you combine enough unusual details, the imagination begins to wander. It's human nature. From there, the sci-fi scenarios write themselves. Some imagine a probe disguised as a comet, using an icy shell as long-term shielding. Others imagine a vault, an ancient archive carrying information from a lost civilization, drifting quietly until someone finds it. A more dramatic idea pictures a seed ship, a vessel designed to travel across vast stretches of time and space, using the cold as protection, waiting to activate when it nears a star. These ideas do not come from fear. They come from curiosity, from the instinct to turn the unknown into a story that feels meaningful. But when you step back into the science, most of these mysteries soften. Many comets have active regions that vent from the same places repeatedly. They are shaped by fractures, pockets, and weak spots that do not change quickly. When the sun warms them, they breathe through the same channels every time. BB is no different, only larger and older. The fixed jets do not require engineering. They require ice, pressure, and a path to escape. The smooth light curve also sounds dramatic until you consider BB's size. Large bodies rotate slowly. Their surfaces are uniform enough that brightness changes gradually, not in sharp jumps. A smaller object tumbles, producing irregular patterns of light. A world-sized body like BB turns with the steady calm of something shaped by its own gravity. That smoothness is what you expect from a nearly spherical planetesimal. Not a signal, not a beacon, just physics. And then there is the orbit. It is strange, yes. It is tilted almost vertically, yes. But both possibilities, an ancient scattering event or a long-ago capture, explain it naturally. The early solar system was chaotic enough to kick worlds in every direction. And the sun was born in a cluster of stars where close approaches were common. You do not need an artificial cause when nature has already given you mechanisms powerful enough to send BB on its current path. None of this means the questions are foolish. In fact, thinking about the artificial hypothesis helps sharpen your sense of what true technology would look like. It helps you understand what kinds of signatures would stand out against natural behavior. It creates a mental framework, the difference between controlled motion and chaotic motion, between engineered rotation and gravitational evolution, between deliberate energy output and sublimation. The exercise itself has value, even when the answer is simple. What if someone wanted to send a message that could survive billions of years? That question floats through your thoughts for a moment, and then it lands gently. You do not need that explanation yet. Not when the natural processes of the solar system already offer an elegant account of what BB is and why it behaves the way it does. Extraordinary claims demand extraordinary evidence. For now, we don't have that evidence. What we have is a world-sized comet, a relic from the birth of the solar system, behaving in ways that are surprising only because objects like it rarely fall inward. Its mysteries are geological and dynamical, not technological. And that is enough to keep you wondering without drifting into anxiety. You begin to feel the calm return, the steady reassurance that no doom, No hype and no hidden threat lies behind this story. Just wonder, curiosity, the pleasure of asking questions without needing alarms. BB remains a natural object, extraordinary because of its history, its size, its orbit, and its timing, not because of anything artificial. Whether natural or not, one fact remains. Reaching this object would be almost impossibly hard. When you imagine sending a spacecraft to BB, the idea seems simple at first. You aim a probe outward, let it coast for years, and eventually meet the giant as it falls inward. But the moment you look at the real numbers, the simplicity dissolves. Reaching BB is not just difficult, it is almost beyond what current technology can do. And in that limitation, you feel a quiet sense of regret. The opportunity is real, the window is narrow, the object is extraordinary. Yet the path toward it bends away from what your tools can easily reach. The first obstacle is its orbit. BB approaches the solar system on a path tilted at nearly 95 degrees, almost perpendicular to the planetary plane. Every spacecraft you have ever launched begins its journey from Earth's orbit, which lies firmly within that plane. Changing a spacecraft's path from this plane to BB's near-vertical direction would require an enormous amount of energy. In spaceflight, that energy is measured as delta V, the change in velocity needed to alter course. And the delta V required to tilt a spacecraft by almost an entire right angle is immense, far more than any chemical rocket can supply directly. To make that maneuver remotely feasible, a spacecraft would need to steal momentum from a giant planet, typically Jupiter. By swinging around Jupiter in just the right way, a probe could change direction without burning impossible amounts of fuel. But that introduces another constraint: timing. Jupiter must be in the correct position when the spacecraft arrives, and BB must be reachable afterward. The launch window becomes incredibly narrow. 1 year too early, and the geometry collapses. 1 year too late, and the opportunity has already passed. Even if you could line up the geometry, distance becomes the second obstacle. BB will never approach closer than about 11 astronomical units from the Sun. That is 3 times farther than Jupiter and farther than any Comet mission has ever attempted. Solar panels become useless out there. You would need a radioisotope power source, an RTG, to keep the probe alive. These systems are expensive, rare, and heavily regulated. Building one requires long planning cycles and material that cannot be produced quickly. And then there is the question of autonomy. At those distances, radio signals take hours to travel each way. A spacecraft near BB would need to make decisions on its own, navigate on its own, and respond to hazards without waiting for instructions from Earth. That level of independence is possible, but challenging. It turns a simple flyby into a technical frontier mission, the kind usually reserved for decades of preparation and large budgets. Several ghost missions, as some engineers call them, have been proposed in quiet corners of conference rooms and informal papers. Small probes, lightweight instruments, quick and cheap designs that could hitch a ride on larger rockets and attempt an ambitious intercept. Some include flybys. Others suggest dropping tiny sensor packages along BB's path. None of them are formally funded. None are fully engineered. They exist as ideas on slides, hand-drawn trajectories in notebooks, hopeful conversations during coffee breaks. You can feel the mixture of admiration and frustration in those conversations. Scientists know how rare BB is. They know this is a one-time opportunity. They know they might never see another object like it again. And yet resources are limited. Launch vehicles are booked years ahead. Missions are planned in cycles that stretch across decades. Bringing a new deep space project to life is not just about vision. It is about budgets, priorities, and political will. Sometimes the sky offers you a golden moment that your infrastructure simply cannot reach. That is the soft shock beneath this story. Not fear, not danger, but the quiet disappointment of knowing that even when your imagination is ready, your fuel may not be. Some questions in astronomy are not limited by imagination, but by fuel. You are living in an era when the sky is revealing secrets faster than you can send missions to chase them. That imbalance is humbling, a reminder that discovery often outpaces ability. There is a twist in this realization. Choosing not to launch can itself become a historical decision. Future generations may look back at these years and ask why you didn't go. They may wish you had tried, even knowing the odds were long. But they will also understand that missions are not just dreams. They are engineering challenges bound by reality. And sometimes reality wins. Yet even if no spacecraft ever touches BB, you are not shut out of its story. Telescopes will track its behavior. Instruments will study its jets. Models will project its stress, its structure, its chemistry. BB will still teach you about planet formation, about the early solar system, about the strange population of worlds hidden in the cold. It will still challenge your understanding of gravity and time. It will still reveal more than you expect. Even if we never reach it, the invisible forces that move this object can still be traced. Far beyond the realm of planets, comets, and gravitational encounters with passing stars lies a quieter possibility, one that belongs not to ordinary matter, but to the unseen material that makes up most of the mass in the universe. Dark matter. You never see it directly. You never touch it. And yet every galaxy, every cluster, every cosmic filament is shaped by its presence. If you were to remove it, the visible universe would fall apart. Over the past few decades, gravitational lensing maps have revealed that dark matter is not smooth. It clumps. It forms knots, threads, and strands, structures woven through space like an invisible web. These features guide the motion of galaxies, bend the paths of light, and create small pockets of gravity where no ordinary matter exists. They are real, even if you can only detect them through their influence. Now imagine one of these knots drifting through the outer region of the solar system long before humans existed. It wouldn't collide with anything. Dark matter does not interact with normal matter through light or chemistry. It would pass through effortlessly, like a ghost sliding between atoms. But its gravity, weak, subtle, persistent, could tug gently on the objects it encountered. And in a region as fragile as the Oort Cloud, even a slight pull sustained over many thousands of years could change everything. Picture an invisible mass, moving slowly across the distant edge of the solar system. Objects in the Oort Cloud, orbiting in near-perfect stillness, would feel that faint gravitational whisper. A few trajectories might shift. Some bodies might drift inward. Others might tilt or scatter. Nothing violent, nothing sudden. Just a soft distortion in a region so delicate that gentle forces accumulate over time. If something like that passed near BB millions of years ago, it could have nudged the giant worldlet off its stable orbit, setting it on the long path that now brings it toward the sun, not as a deliberate act, not as a threat, simply as a natural consequence of the cosmic web running through every corner of the galaxy. A dark matter substructure, a clump or filament, leaving its mark not through impact but through persistent gravity. The difficulty, of course, is that dark matter cannot be tracked. You cannot spot it with telescopes, or reflect radio waves from it, or watch it heat or glow. If a dark matter stream passed through the Oort Cloud 1 million years ago, there is no direct signature that reveals where it went or which objects it touched. All you can observe are the outcomes: tilted orbits, odd motions, quiet disruptions in the architecture of distant icy bodies. In that sense, the Oort Cloud becomes a canvas where invisible forces sometimes leave visible traces. And this is where awe seeps into your understanding. The idea that BB's strange journey might reflect not only the history of the solar system, but also the structure of the universe itself. That a body falling inward today may have been set in motion by a river of ghost matter streaming through the outskirts of the sun's domain long before humans walked the earth. It's not frightening, it's quietly humbling. You begin to appreciate the possibility that BB is more than a relic. It is evidence, a witness to events you cannot observe directly, a signpost pointing toward the hidden scaffolding of the cosmos. We may never see the dark matter itself, but we can see what it leaves behind. That idea settles into your mind like a soft echo. If this interpretation is true, then BB becomes one of the rare clues you have for mapping unseen structures near the solar system. Most dark matter features are too large, too diffuse, or too distant to influence anything you can measure locally. But if one of those structures brushed past the Oort Cloud in the distant past, its signature might be encoded in the trajectories of a few world-sized objects, BB among them. In this way, BB connects local astronomy to cosmology. It becomes a bridge between the solar system and the vast networks of dark matter that shape galaxies. Its path may carry hints about how the sun once interacted with the cosmic environment around it, how the solar system drifted through invisible currents, and how those currents left ripples in the outermost regions. BB is not just a visitor, it is a messenger from a deeper structure. To understand how our own system was once reshaped, we need to look closer to home, to the tilt of our sun. Every system carries traces of its past, and sometimes those traces sit in plain sight. One of the quietest but most puzzling clues in our own solar system is the tilt of the sun itself. You might expect the sun, the central anchor of all planetary motion, to be perfectly aligned with the orbital plane of the planets it created. After all, everything formed from the same rotating disk of gas and dust. That disk spun like a cosmic wheel. The planets inherited its motion. The sun should have too. But it didn't. Instead, the sun leans about 6 degrees relative to the plane in which the planets orbit. It is a small angle, just enough to be noticeable, but large enough to raise eyebrows. It is a mystery that has lingered for decades. Why is the sun not aligned with its own planetary family? What moment in deep time nudged it off-center? Clues began to emerge when 2 missions, Juno around Jupiter and Gaia mapping the galaxy, offered new data. Juno measured the internal structure of Jupiter with exquisite precision, allowing scientists to understand better how the giant planet responds to gravitational torques. Gaia traced the motions of nearby stars with unprecedented accuracy, revealing past encounters the Sun may have had during its long orbit around the Milky Way. Together, the data pointed toward an intriguing scenario. Millions or even billions of years ago, a star or a massive object may have passed close to our solar system. Not close enough to disrupt the inner planets, but close enough to tug on the sun and the outer reservoir of icy bodies. A gravitational brush, soft but decisive. Such an encounter could have twisted the sun's rotation axis slightly, leaving it tilted relative to the disk the planets share. And at the same time, it could have disturbed the distant edges of the system, scattering objects, bending orbits, and sending some bodies into extreme inclinations. In that light, BB's path begins to feel less isolated. If the solar system once experienced a gentle but powerful nudge from a passing star, BB might be one of its far echoes. An object lifted into a steep orbit long ago, left drifting in the dark for ages, and only now falling inward where you can see it. The idea does not come with certainty, but it comes with a sense of continuity, a connection between a cosmic close call in the past and a mysterious visitor in the present. There is something nostalgic in this thought, as if you are hearing a childhood story from the solar system's earliest years, a story about chaos and brushes with danger, about moments when the architecture of the system shifted in ways subtle enough to preserve life, but strong enough to leave long-lasting marks. You almost feel the solar system as a living entity, carrying memories etched into its tilt, its orbits, and its distant, icy halo. Our calm sun might be tilted because of a cosmic close call. The idea is soft but unforgettable. It reminds you that even the most stable structures are shaped by events they endured long ago. And it opens the door to a deeper truth. The anomalies you see today, like BB's strange orbit, may not be signs of something happening now. They may be quiet echoes of a disturbance that happened before Earth existed. Those echoes may have had unexpected consequences. A passing star could have destabilized dangerous debris, clearing space for the young Earth to evolve safely. It could have trimmed the edges of the disk, sculpted the distribution of comets, or reshaped the balance of mass in ways that eventually made life possible. A moment of chaos might have laid the foundation for the environment you inhabit now. That is the twist hidden inside the mystery. What once seemed like a threat may have been part of what made your world possible. You begin to sense a gentle gratitude for the ancient turbulence that carved the solar system into its present form. Even violent encounters can lead to calm outcomes. Even disruptions can set the stage for stability. And when you look at BB through that lens, it becomes not a warning, but a relic, a fingerprint left behind by a star that brushed past your home long before the Earth cooled. Somewhere in deep time, a star may have brushed past our home and left BB as one of its fingerprints. And when we zoom out even further, we discover that our story is written on an even larger canvas. When you step back far enough, far beyond the sun, beyond the planets, beyond the Oort Cloud where BB once drifted, you begin to see the universe arranged in a pattern that is both immense and delicate. Astronomers call it the cosmic web, a vast network of filaments stretching across billions of light years. Along these threads, galaxies cluster like dewdrops on invisible strands. Between the threads lie enormous empty regions, supervoids, places where almost nothing resides. The cosmic web is not smooth. It is lumpy, uneven, and filled with contrasts. Dense clusters burn bright with starlight, while supervoids remain hauntingly still. These are not small gaps. Some stretch hundreds of millions of light years across, vast bowls of near-nothingness carved into the universe. They are so large that if you place the entire Milky Way inside one, it would barely register. The universe is structured around presence, but also around absence. One of the most intriguing of these absences is the cold spot in the cosmic microwave background, the afterglow of the Big Bang. When astronomers mapped that faint radiation, they expected it to be nearly uniform, like a warm fog gently cooling. But the cold spot stood out, a region significantly colder than the surrounding glow. Its existence sparked decades of debate. Was it a statistical fluke, evidence of a supervoid in that direction, or a sign of something even stranger, some relic imprint from the early universe that standard physics couldn't quite explain? Supervoids may contribute to the cold spot. Their lack of mass can alter the path of light, draining a little energy from photons as they cross. But even the largest known supervoids cannot fully account for the anomaly. Something about that cold region remains unresolved, lingering in the background of cosmology like a soft bruise on the earliest light we can see. As you listen, a gentle emotional parallel emerges. The universe is not perfectly even. It has scars, dents, low places where something long ago went strangely quiet. Even the cosmic microwave background has a cold whisper where something long ago went strangely quiet. And somehow that makes the universe feel more familiar. Not a flawless machine, but a living structure shaped by events we only partly understand. This is where BB fits into the larger picture. The strange orbit, the long inward fall, the deep history written into its layers. They are not oddities in an otherwise tidy cosmos. They are part of a universe where large-scale structures twist space, where dark matter forms invisible rivers, where supervoids stretch like enormous hollows in the cosmic fabric. The weirdness of BB is just one small echo of the universe's much bigger weirdness. You feel something shift inside you, not fear, but acceptance, a sense of being very small, yes, but also gently held within a structure far older and grander than the solar system itself. The universe is full of mysteries, and yet you're able to watch one drift inward from the shadows. You are part of the same story, made of the same atoms, shaped by the same physics. The twist, if there is one, is subtle. The emptiest places in the universe may hold the clues to some of its deepest secrets. Just as BB, quiet, ancient, overlooked, carries clues about the forces that shaped your own system, supervoids may carry clues about the forces that shape the cosmos. Emptiness is not meaningless. Sometimes it is information waiting to be understood. By the time you reach this point in the journey, you find yourself ready for the conclusion. You are ready to let go of the need to solve every puzzle, ready to rest inside the simple truth that wonder does not depend on certainty. You can appreciate the fragments of knowledge you have, the mysteries you do not, and the calm that comes from sitting between the two. So what does this mysterious, far more sinister visitor really mean? For science, and for you, lying here tonight. As the journey comes to its end, everything you've learned about BB begins to settle into place. Facts, debates, and the gentle speculation that makes the universe feel alive. You've traveled from the icy outskirts of the solar system to the cosmic web itself, tracing the path of a world that almost became a planet, a world nudged long ago into a strange orbit, a world now falling inward where you can finally see it. And through that long arc, 3 layers of understanding have emerged. The facts are simple and steady. BB is enormous, far larger than any comet usually found drifting inward. Its path is tilted nearly 95 degrees, as if lifted by an ancient encounter. Its structure is layered like a frozen onion, with pockets of hypervolatiles deep inside, and its timing is remarkable. A giant worldlet slipping into the inner solar system just as humans have the tools to observe it carefully for the first time in history. Then, there are the debates. Ideas about what could have perturbed BB long ago. The possibility of Planet 9 shaping distant orbits. The idea of phantom perturbers or dark objects moving invisibly through the outer system. The memory of a passing star twisting the sun's tilt and disturbing the Oort Cloud. Even the whisper of dark matter streams leaving faint gravitational fingerprints that only an object like BB could reveal. These debates do not demand immediate answers. They simply open doors, inviting you to look at the broader environment in which the solar system lives. And finally, the speculations. The unfinished world identity of BB, the fantasy of an artificial origin, whispered about but never supported by evidence. The thought that BB might be an echo of a cosmic accident from before Earth formed. These ideas add softness, imagination, and depth, not to frighten, but to remind you that wonder is part of science too. All 3 layers, fact, debate, speculation, settle gently now. None of them ask anything of you. None of them require solving tonight. Tonight, none of these are problems you have to solve. You can let them drift like distant lights on the horizon. Interesting, but not urgent. Beautiful, but not heavy. You can let the sun remain tilted the way it has been for billions of years. It doesn't need straightening. It doesn't need explaining tonight. It only needs to shine, as it always has. You can let BB continue its long, slow fall inward. It is not a danger. It asks nothing from you except a moment of curiosity. It has traveled for millions of years to reach this place in time, and you are merely watching it pass. You can let the universe keep its secrets a little longer, not because the secrets are frightening, but because they are vast, patient, and not meant to be rushed. Sometimes knowledge arrives quickly, like a spark. Sometimes it arrives slowly, like a world drifting from the cold. You are allowed to rest while the universe keeps working in the background. And now, the picture softens. You imagine yourself lying on a small boat, drifting across a calm, dark ocean of space. The stars are quiet above you. The sun is a warm lantern in the distance. And far beyond that, BB moves with the same unhurried rhythm, its frozen jets whispering gently into the dark. You feel small, but not lost. You feel held, as if the universe has room for you, even among objects older than memory itself. You don't have to hold the whole universe in your mind. Tonight, you only have to rest. That truth settles over you like a blanket. Awe dissolves into calm, curiosity into comfort. The journey that began with a giant, sinister object becomes something softer, a reminder that you are safe, and that the cosmos is not a storm you must weather, but a landscape you can drift through without fear. The final realization arrives quietly. The most sinister thing was never the object itself. It was the mistake of thinking you needed to control every mystery, solve every puzzle, or understand every force at play. You don't. You never have. You're allowed to let the universe be vast and let yourself be small within it. The universe is under no obligation to be simple, and you are under no obligation to solve it before bed. Close your eyes. Let the mysterious object keep falling through the dark. Let the sun keep shining. You are safe. The universe is quiet enough for you to sleep.